Yes. Um, so my presentation is over mitigating environmental impacts of copper mining, sustainable practices for metal extraction. So copper is essential for technology, construction, and renewable energy systems, but traditional extraction causes major land, water, and air impacts. And today I'll focus on these impacts and two more sustainable solutions, which is bioleaching and copper recycling, with examples tied to the Escondida mines in Chile. So this map shows the Escondida mines in northern Chile, which is the world's largest copper mine. It's a good example because it produces huge volumes of ore and faces long-term issues such as water use, tailings, and energy demand. And understanding this location helps connect global copper demand with real environmental impacts. And then the little red star is where the mines are at. And I'm not really too sure if I did this map app correctly, just because I was having a hard time with that. But yeah.
That's pretty
So,
good.
okay.
Looks
So,
like northern Chile to me.
okay. Um, and then here we have a figure of environmental impacts of conventional mining. So traditional copper mining begins with clearing land for open pit mines, and this causes deforestation, habitat loss, and erosion. And the pit generates huge amounts of waste rock and tailing, which often contain heavy metals and sulfides. These tailings can contaminate groundwater and rivers. Melting requires extremely high temperatures and releases CO2 and SO2, contributing to greenhouse gases and air pollution. And then mines like the Escondida generate millions of tons of tailing each year, so the environmental footprint is significant. Here we have a figure of acid mine drainage. So acid mine drainage happens when sulfide-rich rocks react with oxygen and water. This produces sulfuric acid, which dissolves metals like copper and iron. And then the acidic, metal-rich water flows into streams and rivers, harming ecosystems. And then the acid mine drainage is one of the most serious long-term risks from copper mining. This is why sustainable extraction methods are important. They help reduce the amount of sulfide waste that can generate the acid mine drainage. And then here we have a figure of bioleaching. So bioleaching uses bacteria instead of high temperature smelting to extract copper. The bacteria breaks down sulfide minerals and releases copper into solution. This method produces far fewer emissions, uses less energy, and requires less land disturbances. It is especially useful for low-grade ores, which is the US and Chile both have this. Bioleaching could reduce environmental pressures at large mines like Escondida. Here we have a figure of conventional mining versus bioleaching. So on the left, conventional mining involves open pits, heavy machinery, and smelting, all of which increase CO2 emissions, creating tailings, and disturb large areas of land. And then on the right, bioleaching operates at low temperatures, creates minimal waste, and avoids smelting emissions entirely. So overall, bioleaching is a cleaner, lower impact alternative for copper extraction. Here we have copper recycling. So copper recycling keeps metals in a circular loop. Scrap copper from electronics, buildings, and wiring is collected, sorted, shredded, melted, and purified. This process uses up to 85% less energy than mining new copper, and recycling reduces the need for new land disturbances, tailings, and smelting emissions. And then it also increases recycling, would reduce the pressure on major mines like the one in Chile. So here we have the environmental benefits of traditional versus sustainable methods. So traditional mining uses large-scale blasting, smelting, and waste disposal, creating high CO2 emissions, tailings, and land disturbances. Sustainable methods like bioleaching and recycling lower energy use, reduce emissions, and produce minimal waste. For massive operations like the Escondida mine, Even partial adoption of sustainable methods such as improved water efficiency or bioleaching for low-grade ores could greatly reduce the environmental impacts.
Just want to preface, I am a little bit sick right now, so it might be a little bit nasty, but
Sorry about that.
yeah, so basically I'm talking about lithium production in the United States and why our current lithium production is a little bit of a problem and how we can increase our lithium production and some new things that have come out recently with our lithium reserves and deposits. Yeah, so overall global demand has increased pretty significantly over the past 5 years, and the price especially has significantly increased. Before 2020, the price was probably half of what it is now, so around $7,000 a ton. It peaked in 2023 at $80,000 a ton, and now it's kind of stabilized around $14,000. And the graph on the right is showing the global projected demand into 2035, which seems like a pretty linear trend, but going from less than 500,000 of tons demand to over 3.5 is a pretty big increase. So we're definitely going to have to rise to meet that goal. And stuff that this is used for is the big thing is not actually EVs. It's modernizing our power grid and having battery storage within it, which is something that the US, I know, especially here in Texas, we know that the power grid kind of sucks, right? So making that better and more stable is a really important thing that's going to be coming up in the next decade, as well as EVs, phone batteries, all those good kinds of things. So the issue right now is the United States heavily relies on importing lithium, including other critical minerals from other countries, but we're only talking about lithium here. And if you look at this graph, this is the share of global lithium mined in 2023. If you look on the right, United States is about 1% of the global share, and Australia, Chile, and China make up like, I think it was like 85%, and all the other countries combined make up the other like 10 to 15, right? And the U.S. has a lot of lithium. We'll get to this later. The United States is actually like fourth in total lithium reserves, and we're eighth in how much we produce. So this is showing our current U.S. lithium deposits, and it's the GeoMap map. And these black things, they're not just deposits, but they're deposits that we're mining. And most of the deposits that we're currently mining are actually hard rock deposits. So there's stuff like pegmatites or they're volcanic clays and stuff. We're not doing a whole lot with brines like in the Smack-Over formation right now. And so this graph on the right is showing the breakdown of our reserves and what we actually have. So you can see most of it is volcanic sedimentary stuff, which is like clays, pretty solid amount of hard rock, and then evaporative brine is also rock or like a different kind of brine than the brines we're talking about here. So the brines I'm talking about is oil field brines and then just geothermal brines. So like the Salton Sea Formation and the Smack-Over Formation, both are really good sources. And even though it's the smallest part of it, it's still a pretty significant aspect of our lithium reserves that we're not really exploiting at all. So the other big thing is we just found this new deposit on the Nevada-Oregon border called Thacker Pass, which is another volcanic deposit, which is super enriched in lithium. It's about 3 times more enriched than other similar deposits. And our total U.S. reserves right now is around, that's a wrong figure. It should be more than that. Should be more than 1 million. But the Thacker Pass increased our total reserves by 3 million. So how lithium extraction from oil field brines works is basically you'll have a reservoir and you're pulling like wastewater or you're pulling these brines up from this reservoir. And then there's a few recovery systems that you can use, solvent extraction, adsorption, electrolysis, and membrane separation. There's varying levels of efficiency when extracting this lithium and also the energy cost of actually having to pull it out. And when it comes out, it's either an Li2CO3 or LiOH. So you need a little bit of further refinement from there if you're going to use it in industrial applications. And then in the industrial application, it's batteries, alloys, and ceramics are the big 3 that lithium's used for. So I'm going to talk about here in Canada, there's a big company called E3 Metals, and they're big into this brine extraction, and they have a new system that's supposed to be even more efficient than the previous one I talked about, but they wouldn't comment on what it was because it's like proprietary information. But this is their system for how they're able to pull lithium, and they call it petrolithium because it's oil and gas brine lithium. And in one of their reservoirs, they're projecting 6.72 million tons of lithium that they can refine over like the operating period. So it kind of kills two birds with one stone. If you already have these reservoirs, wells drilled into them, you can use the same wells just to pull out the same fluid, get your lithium out of it, and then pump it back into a injection wastewater well. So pretty effective. Yeah, and so for our projected increase in lithium production, like I said earlier, we actually have a lot of lithium, and this graph is from 2022, so it's not showing that new Thacker Pass reserve that we got. We have about the same amount that Canada does, and Canada's production was a lot higher than ours. So the U.S. can significantly increase its lithium production, not only through mining more hard rock or clays, but also through this like taking it from the brines, right? And especially in Texas with this macro formation, which runs from like East Texas to Oklahoma, pretty much. There's a huge opportunity there in order to pull more out of the ground, which could be very big for geologists in the coming decade or so. Yeah, those are some of my references. The one thing I will say, the map data that I got was from USGS for where the lithium mines were. Some of these articles are pretty interesting as well. So, yeah, that's it.
Questions?
All right. I'm Luke Frazier. I'll be talking about the Ring of Fire. This picture here is completely a misdirection. So as geologists, I'm sure when y'all hear Ring of Fire, you think of the Pacific Ring of Fire, which I have kind of outlined a little bit in that red outline to the left. Pacific Ring of Fire has, of course, the majority of Earth's currently active volcanoes and earthquakes. It kind of wraps around the Pacific where subduction is happening. But the Ring of Fire that I'm talking about today is actually in northern Ontario. And it is a region of mineral deposits. So it's that little red circle kind of towards the right. And you can see it's actually pretty large. And the true extent of possible mineral resources is even still a little bit beyond that circle. Yet there are a number of challenges that have kind of kept any resources from being mined in that area. And we'll get into those at the end of the presentation. All right, so now we are down to the level of that little circle that y'all just saw. And so I told you this was a region, not just one mineral deposit. And the name Ring of Fire really is mostly in reference to this McFaulds Lake greenstone belt of Archean bedrock. The bulk of the area is made up of felsic to intermediate intrusive rock. There's a smaller area in the purple of mafic to ultramafic intrusive rock, and then in the green, some metamorphized volcanic and sedimentary rocks. And then there are two areas here with the most economically significant mineralization, as has been explored thus far, at least. There's the Ring of Fire intrusive suite, which is that black outline inside the circle, and then there's the High Bank Fish Trap intrusive complex to the south in the white outline. So I think it's been said a few times in this course that mineral deposit types can kind of sometimes blend into each other a little bit. And here we can certainly see that there's a good number of different deposit types in this region, probably mafic layered intrusions being the best fit for the mineralization of highest value. These mafic to ultramafic rocks deposited significant resources through orthomagmatic crystallization, if y'all remember that term. But there are a ton of other deposit types here. There's some iron oxide apatates and the more felsic rocks, possibly some iron oxide copper gold mineralization, some intrusion-related gold systems, and some sporadic VMS deposits as well. But the main mineralization in the area that the area is known for is the mafic metal-rich intrusions. So what kind of minerals and metals do we even have in this area? Well, the most significant is high concentrations of chromium. And those are found in that really small red area right in the middle of this greenstone belt. It's an ultramafic section, and being a mafic layered intrusion, there's not just chromium, but there's a little bit more. There's also some nickel copper PGE mineralization in the same area in that red. There's also some iron, titanium, vanadium mineralization in the mafic areas of the Ring of Fire intrusive suite, and also in the High Bank Fish Trap intrusive complex in the yellow. The High Bank Fish Trap intrusive complex also has some iron, copper, nickel mineralization. And then there are a few VMS deposits identified in the darker green areas that contain nickel, copper, and some heavy rare earth elements, though it hasn't been made public just how concentrated or widespread these rare earth elements are. There's a lot of potential for other resources in the area, but these still need a lot more exploration. So possibly more nickel, copper, VMS deposits, potential iron oxide, copper, gold deposits, which I mentioned earlier. And then there's one sample from a felsic rock unit that had a uranium content of 107 ppm. So some companies are definitely going to look more into that and if there's any more uranium in this area. Now, not on this map is a lot of gold mineralization in different faults. And the initial reason that this area was explored was for diamond mineralization, which is spread out mostly in the felsic units. So the area is still undergoing exploration to determine the true extent of economically significant areas and exactly how much metals can be extracted from them. Now, of these metals that have been identified, all of them are labeled as critical minerals by the Canadian government. The US is also interested in the development of this region, as it would greatly benefit our supply chain as well. In all of these, except for iron, you can see because iron goes red, white, red. All of these but iron are also recognized as critical minerals by the United States, and we would likely be involved in the processing of any extracted ores. The economic impact of mining in the region hasn't been fully determined, but estimates state that it would generate over $22 billion for Ontario's economy over about 30 years. Now you're probably thinking, $22 billion. Why have they not started tearing this ground up yet? And well, with any mining project, especially in a more developed country, there are laws and conditions that need to be met. The first set we'll look at is environmental challenges. The Ring of Fire falls within both boreal and peatland ecological zones, which are some of the world's largest, and they contain somewhere around 35 billion tons of carbon. The Ring of Fire also falls right within the middle of a caribou range. Caribou in Canada are endangered and, of course, rely on the availability of non-polluted boreal and peatland environments. And First Nation communities also rely on these endangered caribou, so any mining impact on their population needs to be justified before development begins. The biggest challenge, however, probably comes from the First Nations community and a lack of any all-season roads within several hundred kilometers from the site. First Nation communities, specifically the Webequie and Martin Falls, do have the desire for the area to be mined, as it would open up jobs for their people and also improve their economy. However, they want it done right. And the Canadian government hasn't yet met their standards for an economic impact assessment on how exactly mining would improve things, what we can get, how much, and also environmental impact assessment hasn't been met to their standards. So more detailed exploration results and environmental impact needs to be addressed first before the First Nations will sign off on any mining activity. However, both of those First Nation communities have agreed for roads to be built. And the Canadian government has started construction on these. It'll cost a little bit over $1 billion to install the necessary infrastructure, and it'll take a few years to reach completion. However, it is a good first step to getting the area prepared for resource extraction that will hopefully benefit Canada, the First Nations, and even the United States. So that is the end of my presentation. Most of my maps are made through ArcGIS Pro with some data from ArcGIS Online, but the bulk of the data was from that first reference there. And yeah, any questions?
Okay, I wanted to look into the rare earth possibilities in Texas. That's why there's a question mark. Is there really any out there, and are they economical? And just led to the second question, does Texas really become a metal mining state? And actually, that's false, because it already became a metal mining state in October or November once it started producing some uranium. But and this is just a quick, what I'm sure everyone knows, but what are the rare earths out there? There are the 15 lanthanides, scandium, and yttrium out there. The lanthanides are the ones that have the F orbital in the atomic shell. Scandium and yttrium are and smaller chemicals out there. I briefly went through and looked at all the elements, their abundance, and the lithosphere and parts per millions, their uses, current production levels, briefly, and got some of that data not completely filled out, but certainly rare earths are one of the hottest topics on the planet right now. And it's probably going to remain that way for a few years, and because of China and their control over it. But when I sit back and look at all this data on the production levels and the abundance out there, honestly, I have a hard time seeing where it's going to be a problem long term, with the possible exception of Europe. Europe kind of knows it's screwed right now. But when you sit back and look at helium, which is 1 part per million, and one of the, it's used in laser surgery, permagnetics, great demand, probably growth coming down the road, but it's still 20 times more abundant than silver out there. It's hard for me to imagine these will really be an issue and problem once the industry puts their capital to work and starts developing these resources. One present project in Texas is called Round Top. I know all our maps and things are supposed to be hand-drawn out there, but I want you guys to understand the play better, so I'm using real pictures and photographs. I think you'll understand it much better. It was started and originally leased in 2011 by a company called Texas Mineral Resources. And even essentially 14 years later, it's still not developed. It's a small hill or mountain out in Hudspeth County. On this map, you can see Interstate 10, and at the very northwest corner of Interstate 10, that would be El Paso out there. So it's about 80 miles southeast of El Paso. You'll see 5 black dots on that thing. There are purple lines pointing to 4 of them, and 4 of those have been surveyed for the rare earth minerals. Little Round Top was the highest, or no, I'm sorry, Round Top was the highest. It's 560 parts per million. And so that's the one that's currently going to be developed. It's interesting. It makes economic sense. It's because it's right near Interstate 10, and it's also right near the Union Pacific Railroad line. So it's easy to move the ore out of there to be processed somewhere else. Anyhow, and so it's interesting from my standpoint too, because it was such a small lease that covers this. It's only 950 acres out there. It covers the whole deposit. There's a picture of it right there. It's a surface exposed rhyolite intrusion. It's actually a laccolith, 2 miles in kilometer and 375 meters in height. By laccolith, that means the deposit was made underground, but it's been exposed to the surface subsequently then. Mass is estimated at 1.6 billion tons. It's enriched in yttrium.
Yttrium. It's called yttrium.
Yttrium. Okay, thank you. So, and all the heavy rare earth elements, which is interesting because the only one big play we've got in Mountain Passes is in California. That's all light rare earths, and obviously the heavy rare earths are much more rare than light rare earths. The other thing that makes it interesting is there's really no overburden in this, so they just go out and rip that mountain down until it's about flat with the ground, and so it's fairly cheap to develop if it happens. 90 to 95% of it's potassium feldspar, plagioclase, and quartz, and so essentially it's real easy to separate. The rest is a fluoride, potassium fluoride, is a yttrium, Bob step in. Y-bearing fluoride. Yttrium. Y-bearing in my language going forward. So, but anyhow, because of that, you can take sulfuric acid or an acid and leach this stuff pretty easily, and you'll end up with the gang. 90-95% separates from all the stuff you want to keep and separate down the road. But I'm not sure. It's interesting because the company that's really in charge of this isn't Texas Minerals anymore. It's a company called USA Rare Earths. We'll talk more about them down the road. But they're raising money right now, so they're not talking. They pulled all their information from their website. So I'm not really sure what they're going to do, if they're heap leaching this or they've got some new extraction technology, which is called CIX-CIC. So we're not really sure. There's a beryllium deposit at the base. And what makes it interesting is there's some other nice elements that you can sell too. Gallium, uranium that they have, neodymium, one of the light rare earths. And so it could be pretty profitable if you can separate this thing efficiently. So then to me, then that leaves the question, are there more out there? And so we basically went out and pulled the USGS map of the rock units in West Texas, and you can see all the purple dots. Oh, I didn't really do the slide right. I didn't. But those are all the rhyolites, the purple. So you can see at the very kind of on the very edge towards the north, not the northernmost one, is Round Top out there, but you can see there's a ton of other rhyolitic intrusions. And so I think there's got to be a lot more rare earth potential in Texas. In fact, actually last night after I submitted this, I noticed there was a large discovery made in Brewster County, which is to the south of Hudspeth County, where Round Top is. So geologically, everyone talks about this happening in 2 episodes. It's really 3 episodes, but essentially as the Farallon plate was being shoved underneath the North American plate, you had the early phase of volcanism out there, and that was 48 to 42 million years ago. It was silic to mafic intrusions, lava flows, and caldera eruptions. The next phase, which is really where the rhyolitic one was set up, was in the second phase, 38 to 32 million years ago, when they had a lot of same types of intrusions, but voluminous ash flows out there. But the compositions were more alkalitic to alkali. And this was the most active period. And then the last period of volcanism occurred about 24 to 17 million years ago, when the basin range started extending, and the Rio Grande Valley Rift developed, and so that set up the third and last round of volcanism in the area that brought these heavy rare earths to the surface. I guess I didn't really totally missed it, but the company that bought this originally in 2011 was a company called Texas Minerals, which we mentioned before. In 2018, they brought in a company called US Rare Earth as their partner. Texas Minerals never put another penny into this, so it makes me wonder if they really think it's developed or not, but US Rare Earth continues to put money into it. They're based out of Stillwater, Oklahoma, and they're just built their first magnet producing facility. It's about 300 metric tons up in Stillwater. It's supposed to be commissioned in the first quarter, 600 metric tons, I apologize, in the first quarter of next year, and then they're going to double that capacity in the second half of next year. So it's really starting with the downstream product first, building magnets, and then hopefully they're going to be able to provide the sources for the raw materials for those magnet factories from this discovery out there. This is a real company that's brought in the lady that ran Siemens USA. I mean, flip the next slide. So But you can see just kind of the time frame, and probably should talk more about this on the last one, but USAR came in and opened up their first test facility in Colorado in 2020, and that was to see if they could separate all the heavy rare earths out from each other and the gang out there. They announced favorable results, but none of it's public information out there, so you don't know how much is true or not. But this year, in September 29th, they raised over $125 million in a private placement. They brought in Barbara Humpton, who was CEO of Siemens, as their CEO. And then they bought a company out of the UK called Less Common Metals. Less Common Metals is a big processor. I think it's the only one outside China that processes a lot of these rare earths. And so they got to go forward from here. So they should be up producing magnets starting next year. But really, we've got a long ways to go on Round Top to see whether it's going to be completed or not. They just completed the flow sheet. They've got to conduct a pre-feasibility study on the economics of it, whether it makes any sense. That probably, I don't know, I'm making it up. It's probably at least a year is my guess. And then they need to build a pilot plant, which is $50 million. They'll probably do that in Stillwater and test the technology. And as someone that was involved in a pilot plant 40 years ago from Monsanto, I know a lot of times they don't work out. So we'll see. But then once you get proved at the pilot plant, then you got to take it to the bank. So mine construction starts. So I don't think we're going to see production out of this facility long until after their leases expire in 2030. Doesn't mean the leases won't be renewed. I'm sure they will. But it's interesting, and it's a question mark whether it ever really happens or not. And that's what I basically go through in the end is, what are the pluses and minuses? Will we see any heavy rare earth out there? It's clearly a critical issue with the U.S. administration and the Department of War out there. You can see how much money they're spending to fund tons of companies, from the antimony companies in Alaska to Nova in Australia to MP Materials in Las Vegas and Fort Worth out there. There are very few heavy rare earth deposits outside China, so that's clearly an advantage to these guys. In fact, if you go back and look at the minerals and their prices today, they'd make a lot more money out of terbium, selling terbium, than they would in some of their heavy rare earths, but they're not planning to even use those in this. It's interesting because their products are mainly light rare earths, but they got a heavy rare earth mine. So it's a little confusing, and that's possible. It's obviously in a friendly jurisdiction to develop it in Texas, typically, I gotta say, but I can tell you, I started reading last night, the environmental community is moving forward and fast on fighting this thing. And so I don't know that we'll ever get approval. So one company says Round Top is critical to their success, USA Rare Earths, but it says it doesn't add, it's not critical. I apologize, I'm stumbling all over here. It has a lot of advantages, but it's not critical to their success. So you don't know whether it's, how important it is to them. The other developer, Texas Minerals, hasn't put money into this in years. In fact, they're doing more investing in silver exploration in New Mexico, which may make more sense. Anyhow, I went back, it was back in 2021 that there's lots of press on this, and it was going to be operational about 2023. Well, obviously it's 2025 and nothing's advanced out there. So I think there's a lot of question marks on whether this gets developed. And a lot of that may have to do on the technology. Is it heap leach mining? Is it being done somewhere else? Or is there the CIC separation technology? And there's no public information on that. So I don't know. If I was going home at night, I'm probably not going to invest my last dollar in this one, but it still seems like considerable potential. If you sit back and look at the amounts of the rare earths, the prices of those rare earths, would certainly be very profitable. So with that, I will stop.
So today's topic is cyanide contamination from Carlin mine tailings in Nevada and its environmental solutions. So, Carlin-type deposits in Nevada are recognized as the world's most important sediment-hosted gold systems, producing a major share of U.S. gold. What makes these deposits unique is that the gold occurs as micron-scale invisible gold, finely dispersed within Arsenian pyrite rather than in visible grains. These deposits are mainly hosted in Paleozoic carbonate rocks and are spatially aligned along major structural trends such as the Carlin, Cortez, and Geshel trends. These structural zones acted as permeable pathways for low salinity, sulfur-rich hydrothermal fluids during Eocene magmatism and basin and range extension. As the fluids interacted with the carbonate host rocks, they caused characteristic alteration styles, that is, sulfidation, silicification, and argillization, which help trap gold and concentrate associated pathfinder elements like arsenic, antimony, mercury, and thallium. Because of the massive scale of mining in this region, cyanide-based gold extraction is extensively used, which leads to environmental challenges, particularly cyanide contamination from mine tailings. This presentation focuses on how cyanide affects the surrounding environment and what sustainable solutions can help reduce its long-term impact. So here is a geomap derived location. I have specifically zoomed out to derive the 7 deposits in Carlin, as can be shown in the figure. In surface environments, cyanide can be naturally neutralized through sunlight exposure, contact with air, and active microbial ecosystems. However, once cyanide migrates downward into the groundwater, it enters a closed subsurface system where these degradation pathways are almost entirely disabled. First, volatilization stops underground. At depth, there is no air-water interface. Hydrostatic pressure keeps hydrogen cyanide dissolved, and there is no atmospheric exchange. Therefore, cyanide remains in aqueous form much longer instead of escaping as gas. Second, photolysis becomes impossible. Without sunlight, the strong metal cyanide complexes commonly formed in mining environments do not break apart. As a result, cyanide stays chemically stable and remains available for transport. Third, biodegradation slows down dramatically. Groundwater environments are typically low oxygen, nutrient limited, and cold, which reduces microbial activity needed to metabolize cyanide or convert it to less harmful compounds. This means biological breakdown that might take days at the surface can take years underground. Additionally, cyanide interacts only weakly with soil and mineral surfaces. So, instead of being filtered out, it travels rapidly downward through the Vadose zone during rainfall, snowmelt, or process water leakage. Once it reaches the saturated zone, cyanide becomes part of the moving groundwater system and forms dissolved contaminant plumes. These plumes can extend far from the source and frequently carry co-contaminants such as ammonia, thiocyanate, and toxic metals released from tailings. This creates persistent contamination that is difficult and costly to remediate and may threaten aquifers used for drinking water, agriculture, or ecosystems. Beyond the hidden threat, cyanide contamination also delivers a lethal and fast-acting impact above ground, that is, killing migratory birds within minutes of exposure. The migratory birds that instinctively land on cyanide-contaminated ponds for hydration and resting are exposed within seconds through drinking, inhaling hydrogen cyanide above water surface, or absorbing it through thin permeable skin of their webbed feet. Once cyanide enters the bloodstream, it rapidly distributes to vital tissues and binds to the Fe3+ center of cytochrome C oxidase in mitochondria, instantly halting oxidative phosphorylation and causing histotoxic hypoxia. Birds, especially during migration, have extremely high metabolic and oxygen demands. Therefore, the collapse of ATP production results in rapid failure of brain, respiratory system, heart, and neuromuscular coordination. This cascade produces a highly characteristic observable sequence. First, rapid lateral bill shaking, indicating immediate neuromuscular distress, followed by neck muscle weakness as hypoxia progresses, causing the head to droop into the water and often leading to drowning even before peak toxicity. And finally, terminal wing flapping, a brief agonal motor response as respiratory muscles fail completely. Because these processes unfold within minutes, birds frequently die while floating on the pond surface, making cyanide poisoning one of the most fast-acting and lethal toxicological threats at gold mining sites. Next slide, please. Cyanide contamination at mining sites is not confined to water. It also becomes a significant air quality concern when dissolved cyanide in ponds, tailings, or process solutions is converted into hydrogen cyanide gas, a highly volatile and toxic compound. The key reaction driving this transformation is shown in the slide. Cn- plus H plus gives HCN in gaseous form. When cyanide-bearing water becomes even mildly acidic, hydrogen cyanide forms and volatilizes from the surface. Conditions common at gold mines are warm temperatures, strong sunlight, large exposed water surfaces, and windy weather, which greatly increase this gas release. Once formed, hydrogen cyanide readily escapes into the atmosphere because it has a low boiling point and high vapor pressure. Wind enhances this process by breaking the boundary layer on the pond surface, allowing more gas to escape. At the same time, physical disturbances and evaporation can produce airborne dust particles and aerosols that contain cyanide residues. These particulates, generated from dried tailings or splashed pond surfaces, are easily lifted by wind and can travel considerable distances across arid landscapes of Nevada. After entering the air, HCN gas disperses rapidly due to its light molecular weight, while cyanide-bearing dust particles remain suspended and can be transported regionally. Atmospheric degradation of HCN occurs only slowly under sunlight, meaning that cyanide can persist long enough to affect downward wind air quality and deposit onto soil and vegetation far from the mine site. The gas can also interact with other atmospheric pollutants, such as nitrogen oxides or combustion products, contributing to a broader toxic burden. For humans, chronic low-level exposure to airborne cyanide can affect thyroid function, the nervous system, and respiratory health. So, the solution one is using activated carbon, which removes cyanide through a powerful combination of physical adsorption, chemical surface complexation, and catalytic oxidation, making it one of the most versatile and effective treatment options. Its extremely high internal surface area, composed of millions of interconnected micropores, rapidly traps both free cyanide ions and dissolved hydrogen cyanide, which diffuse into the pore network and become immobilized on the carbon surface. As can be seen in the reaction, C plus Cn- gives CCN, and C plus HCN gives CHCN. Beyond simple adsorption, activated carbon contains oxygen-rich functional groups, such as hydroxyl and carboxyl, that chemically interact with dissolved metal cyanide complexes, commonly found in gold tailings. Complexes, such as ZnCN4 2- partially dissociate, releasing both Cn- and metal ions. The liberated Zn2+ binds strongly to negatively charged surface groups on the carbon, which can be seen in the reaction. CO- plus Zn2+ gives COZn+, creating positively charged sites that subsequently capture additional cyanide through COZn plus Cn-, which gives COZnCN. This two-way process not only removes free cyanide, but also destabilizes and immobilizes otherwise persistent metal cyanide complexes. At the same time, the carbon surface promotes the catalytic oxidation of cyanide to far less toxic cyanide. That is, Cn- plus O2 gives OCn-, a reaction that proceeds more efficiently on carbon due to its large surface area and electron transfer properties. Cyanide then undergoes hydrolysis to form ammonia and carbon dioxide. That is, OCn- plus 2H2O gives NH3 plus CO2, completing the transformation into significantly less harmful species. The second environmental solution is destruction using hydrogen peroxide. The core reaction is the rapid oxidation of free cyanide to cyanide, according to Cn- plus H2O2, which gives CnO- plus H2O, a pathway that dominates when pH is maintained above 9 to keep cyanide in its ionic form and prevent acid dissociation reaction Cn- plus H+, which gives HCN in gaseous form. This generates volatile hydrogen cyanide and creates severe health and environmental hazards. Once cyanide is formed, it undergoes the hydrolysis reaction shown on the slide. CnO- plus 2H2O gives NH3 plus SCO3-, producing ammonia and bicarbonate, and thereby transferring the nitrogen load from an acutely toxic species to a less harmful but ecologically significant compound. The slide accurately includes the further oxidation pathway. CnO- plus 2H2O2 gives NO3- plus CO2 plus H2O, illustrating how excess hydrogen peroxide can push cyanide toward nitrate. And also notes that nitrate is not necessarily the final form, because biological processes in slurries or downstream water systems can reduce nitrate to nitrogen gas, as expressed by 2NO3- gives N2 plus 3O2-, completing the conversion to a benign atmospheric species. The slide also highlights two important side reactions: the decomposition of hydrogen peroxide itself, that is 2H2O2 gives 2H2O plus O2, which reduces treatment efficiency, and the copper-assisted liberation of cyanide from metal cyanide complexes, that is CnX n- plus Cu2 plus gives M2 plus Cn- plus Cu complex, which temporarily increases free cyanide concentration, but ultimately enhances overall destruction, because peroxide can only oxidize cyanide once it is released from complexes. Together, these reactions demonstrate that hydrogen peroxide treatment is highly effective and should be carefully managed. So, in this way, we have the references slide, and this is all what I have for my presentation.
Very good. Any questions?
My name is Ryan. I'm going to give a presentation on deep sea mining. Next slide. So first, I'd like to start off by talking about the critical mineral crisis. In order to transition into a clean energy and to sustain a high-tech economy, the U.S. needs to increase their critical mineral supply by 2035. And as of currently, we depend on a fragile global supply chain for processing and refining. So what's our plan for the future? We currently face constraints in onshore processing and recycling, both which are essential, but building that capacity would take a decade or more. We could also build new land-based mines, but face stiff environmental opposition and social challenges. Another option is to turn towards the oceans. This year, on April 24th, the United States government passed an executive order titled Unleashing America's Offshore Critical Minerals and Resources. This order mainly aims to build a secure domestic supply chain for the critical minerals that power everything from electric vehicles to our defense systems. To achieve this, the policy directs federal agencies to accelerate seabed mineral exploration by streamlining permits, encouraging new science, mapping, and technology for the deep sea. So where does all this activity and potential mining actually take place? The targeted resource for seabed mining is polymetallic nodules, which are located on the deep sea floor, specifically on abyssal plains at depths of 4,000 to 6,000 meters. The most well-known and explored region is in the Northeast Pacific Clarion-Clipperton Zone, where the highest concentration of exploration contracts are held. What about the targeted resource? The primary resource being polymetallic nodules. There are potato-sized concretions that form slowly over tens of millions of years. Metals dissolved in seawater slowly precipitate out, building concentric layers around a nucleus, usually small rocks or even shark teeth. Their unique formation process is what makes them incredibly rich in valuable metals. They're made up of manganese, iron, and contain high grades of nickel, cobalt, copper, and rare earth elements. And as you know, these elements are essential for most of our technology and renewable energy systems. To understand why mining these nodules commands global attention, we must first understand the scale of the resource. Current estimates suggest there are roughly 1.7 trillion tons of manganese nodules in the Pacific Ocean alone. Within that, there are roughly 21 billion dry tons of harvestable nodules in the CCZ. That means the total Pacific resource is about 80 times larger than just of that in the CCZ. Now, how do we get from tons of rocks to tons of metals? Using techniques like X-ray diffraction and fluorescence, weight percentages of each metal within the nodules can be determined, and we can multiply that percentage by the total dry tonnage of the resource to estimate the total metal tonnage. For metals critical to our battery and tech future like cobalt and nickel, the CCZ nodules contain several times more than all current land-based reserves. Next slide. So who's at the forefront for mining these nodules? First, we have the Metals Company. They are partnered with Allseas, a world leader in offshore engineering. They have conducted large-scale collector tests in the CCZ back in 2022. There's the Global Sea Mineral Resources, a deep-sea mining subsidiary of the Belgian dredging and marine engineering conglomerate. They've tested their Petania 2 nodule collector on the seafloor in 2019, and again in 2021, gathering critical environmental and operational data. On the state-backed side, we have COMRA, the China Ocean Mineral Resources R&D Association. In July 2021, they announced their successful test of a complete integrated system of harvester and lift mechanism to bring nodules up to the surface. And national research institutes in South Korea and India also hold exploration contracts with the International Seabed Authority and are actively developing their own seabed mining capabilities. But despite all this activity, commercial mining has not started anywhere in the world. These are just tests and trials while stuck in regulatory limbo. No company can begin actual extraction until the ISA finalizes its mining code, which also has no set date for completion. So why should we consider deep sea mining? First, the reduced terrestrial footprint. We avoid many of the destructive impacts of terrestrial mining. There's no need to clear forests and no indigenous lands to disrupt. The sea floor also doesn't require infrastructure such as roads, power grids, or waste dumps typically needed in terrestrial mining. Secondly, simpler extraction. Unlike land-based mines, they don't require drilling and moving tons of leftover rock. These nodules are simply sitting on the seabed. The process is designed as surface collection, which in theory could mean less direct geological disruption and lower energy use per ton of metal. Third, improved human and social conditions. Operations are remote and automated and conducted from ships. This greatly reduces the risk of fatal accidents for workers compared to open pit or underground mines. Furthermore, it prevents serious social issues linked to some terrestrial mining, such as child labor and dangerous mining practices often found in cobalt supply chains. And finally, resource quality. Polymetallic nodules are in fact a polymetallic ore. One resource contains multiple critical metals, and the grades for the metals like cobalt and nickel are often higher than the average terrestrial deposits being mined today. Next slide. There's also many cons in deep sea mining, including sediment plumes and habitat destruction. But one interesting article I found relating to polymetallic nodules is that they can be an oxygen source for microorganisms in abyssal environments. Dark oxygen is an oxygen gas produced in environments that are not light dependent and don't require the photosynthesis process. The researchers that did the study believe that the nodules themselves act as a natural geobattery. As seawater interacts with the different metals in the nodule, it drives a weak electrolysis reaction. But why would this matter? The research suggests that these inert-looking rocks might be biogeochemical hotspots in an otherwise energy-starved desert and can be producing a fundamental resource for microbial life. So by removing these nodules, we'd be shutting down a naturally occurring oxygen factory for an ecosystem we have yet to understand. And that concludes my presentation.
Cool. So today I'm going to be sharing a bit about the alternative methods of metal recovery from mine tailings waters. We know there's a lot of mines in the world. Mine waste around them is a large problem. So kind of utilizing these waters is one step towards kind of reducing this waste problem and creating more kind of circular economy. So these metals from mine waters are typically found on old mine sites. I mean, there are areas that have kind of these tailings that interact with waters and can create these kind of high concentrations of metals within these waters. The metals kind of focused on, I guess, as rare earths. I mean, this photo here is from a mine site I recently visited out in kind of Quebec, and it was an old carbonatite kind of mine, mining niobium, but I can talk a little bit more about that later. So the tailings waters at these sites, yeah, they typically kind of have concentrations of metals kind of interacting with these colloids, and we'll use these different filtration methods to recover them. So this is the kind of the first method that I'll be talking about. It's polymer enhanced ultrafiltration. It is a technique that uses water-soluble polymers to bind dissolved metal ions. Polyelectrolytes interact through electrostatic attraction, while polyclatogens bind metals through coordination with functional groups like amines or carboxylates. So once these polymers bind to the metal ions, the complex will just become too large and be retained by the ultrafiltration membrane, as you can kind of see by the diagram. So this kind of works best in mildly acidic waters, where metals remain in dissolved ionic form, and the method can achieve very high removal efficiencies, kind of like 99% levels for metals like copper, lead, and iron. However, if the waters become strongly acidic, then proton competition reduces polymer metal binding, and if high in particulates, then the membrane can experience fouling, so the efficiency of the membrane reduces. This is the second method. This is nanofiltration. It's a pressure-driven membrane process that can separate ions based on size and charge. So these membranes are negatively charged and are formed of many different kind of materials. It depends on kind of the metal that you're targeting, but these will strongly kind of reject multivalent metal ions like nickel, cobalt, manganese, and rare earths. These are all like 2+, 3+ ions, because this high charge density will attract this kind of large hydrated radius and make it unfavorable for them to enter the membrane pores. Even when this does happen, there's this large charge imbalance that occurs, and the membrane can't pull enough of the anions along with it, so it kind of keeps it electrically neutral. So this keeps the cations on one side, and then these smaller monovalent ions like sodium chloride can pass through the membrane, and eventually when you're passing enough water through the system, you can really concentrate this retentate side in these kind of target metals. This is the third method, called tangential flow filtration. So in this method, you're kind of targeting more the different sizes that are associated with these metals. So these metals often will kind of interact with colloids or large particulates, kind of iron, manganese, oxyhydroxides. These different size kind of particles, they will get captured by these different size filters, as you can kind of see on this diagram. They'll pass through multiple kind of times, and they'll be trapped they'll be passed along this filter, so they won't pass through it, they'll kind of just pass along it, and they'll get pushed back into the retentate and keep reconcentrating. So you end up with this same kind of effect of concentrating the solution in kind of the metals that you're after. And eventually you'll get down to a very fine solution where only kind of ions are coming through it in the 100 kilodalton kind of range. So this is a site I'm working on. It's up near Quebec. It's the one I took a photo at. So it's situated within the Montenegrin igneous province. This is a kind of a chain you can kind of see on the map there. It's a bit hard to see, but there's kind of a chain of early Cretaceous alkaline intrusions. This site was originally a niobium mine. So when they took all this material out, they kind of left over these rare earths in the tailings. So you get kind of very high concentrations in the tailings. So that's another resource that could potentially be reused. But there's also the water. This also has rare earths in, and it's a good site to kind of test out this new method of looking at filtration as a way to recover metals. So this is some kind of data that I've initially got from the site. You can see that some of the sites have got better trends with concentration factors and rare earths. Some don't, and you can kind of see the different pH and different environments. The pH and total dissolved solids at these different sites just kind of show the different environmental kind of differences between the sites, right? So two of them, the top two, these are groundwaters, whereas the pit site, that's a surface water, that's an exposed pit. So you can kind of see the pit waters, they have much lower total dissolved solids, right? So and particulates in the water compared to the groundwaters. Like when I was pumping this water out, you can kind of see the particulates in them. You can see the colloids there. So that itself creates a problem. I mean, even nanofiltration that has its problems of getting pores being blocked, but TFF still has this problem. So this is kind of my theory about what's going on in these different diagrams. You can kind of see the concentration factors in PO13 are much lower versus the other two sites, and this is just because this site here has got many more iron and manganese oxyhydroxides that are kind of at this site present. So when filtering these samples, you can't filter enough water before these membranes start to get clogged up. So it just becomes this less of a pattern that's going on. And you can also see on the right hand side, it's a bit more spaced out than PO26, this site here. I'm thinking this is again kind of an issue of filter clogging. But when there's not this happening, you kind of get this trend with concentration factors increasing with rare earth elements. There's two sites there as well, 2024 and 2025 at the pit. And you can kind of see the difference between the concentration factors and how rare earths also increased by about 10x when you increased concentration factor by 4. But yeah, So overall, we can kind of see that there's no single filtration method that is actually universally effective at this time. It's definitely in this preliminary stage of research where we're looking into it. We're trying to find this kind of solution, and the main things that kind of that matter about this is the pH of the water, the actual site itself, whether there's where these metals are associated with, are they dissolved or are they colloid bound, and the kind of the ionic strength of the system as well, because these all matter depending on what filtration system you're going to use. Yeah, it's a few bit of information there, kind of what deposits they may be working at. I'm not entirely sure, because there's a lot of environmental factors as well, like that can affect pH that aren't just related to the deposit, but these are kind of the main ones that I'd expect these different filtration systems to work at. But yeah, that's everything. Thank you.
So yeah, I'm going to talk about microbial mining, specifically kind of focused on those rare earth elements, just because that's what there's a lot of interest in these days. So I think we've seen this a couple of times, that there's a pretty large forecasted demand, particularly under the current administration, looking for these rare earth elements and trying to make sure that we can onshore and be mining these things locally within the US, as opposed to kind of either importing them from other countries or exporting our mine tailings, so that way other countries can then refine them and send them back to us. I took this slide from, I think, one of Bob's during the lecture. I just found it really interesting to think about, like, we call these rare earth elements a lot of the time, but they're not actually all that rare compared to some of the other elements. It's just sort of a question of how are they distributed and what is their concentration within the different rocks or ores. So current kind of recovery process, we have a couple of key issues. One is just you're using a ton of acid to extract these minerals. There's often a lot of different processing steps where each step needs to be controlling kind of the redox state of the solution, as well as other kind of chemical concentrations. You use a lot of chemicals, which is both expensive and creates this toxic waste effluent. You don't even necessarily get a huge percentage of the elements out. And then because everything is really deposit specific, like you need to tailor your approach to the specific kind of chemical composition, that adds to the cost, because you can't just sort of set it and forget it or have a process that you can repeatedly use. You have to have like a bespoke process for each mine, which just makes it kind of more expensive and challenging as a whole. So one thing I've been looking into is this non-conventional recovery, which is where you use bioaccumulation using mixotrophic biofilms. So mixotrophic just means you kind of have a variety of microbial metabolisms occurring. Here with biofilms, we often see that you'll get metals trapped in the extracellular matrix. So if you kind of picture a bacteria living, and now picture like a bunch of bacteria around them, they'll often do something called quorum sensing, which is where they can become aware when there's a high concentration of bacteria, and then they start to develop these biofilms, which is just sort of a lipid polymer outside of the cells that can start to accumulate. It's used for a variety of things, but one thing it can be used for is to accumulate these metals. Specific strains have been shown to actually hyperaccumulate rare earth elements. And then we also just see kind of a general non-specific accumulation. I'm not sure how big the graph is, but if you can read it, you can kind of see that it's comparing the concentration of dissolved metals in the background seawater to them when they're bioconcentrated, and looking at what amount of concentration or what magnitude of concentration we get using different strains of algae. And then up on the top right is just some different pictures of algae and the type of raceway ponds they've been using, or not raceway ponds, just the different incubation methods they've been using to test these processes. And so there was a really interesting paper that was referenced in an earlier lecture, just kind of talking about how we don't actually need kind of new mines or to be importing a lot of these elements. There's a ton of unrecovered byproducts that are still available within either the mines themselves or within the tailings that we could be using to mass demand. So this is from the Holly 2025 science paper, and they're kind of looking at both global production across all these different elements, as well as US imports, and what is the kind of availability of these unrecovered byproducts. And obviously we can't expect to get 100% of the unrecovered byproducts, but if we could even get a few percentages, it would go a long way to kind of ameliorating our issues. So in addition to sort of adding this as a step for current mining processes, you can also go back over coal ash and start to try to pull out rare earth elements. They're often really, there's higher concentrations of those, typically in the like Appalachian coal areas. There's a lot of promising materials in mine tailings. This is also, if we can get these kind of microbial mechanisms to work, because of the flexibility of microbes, you can sort of drop them in a variety of places. So this could also be used for wastewater and electronics recycling. Someone mentioned earlier that microbes have their own kind of optimal pH range, and that is true, but they also, like different species and strains, can grow across a large percentage of the pH scale. So we have microbes that grow from like a pH of basically 2, and then you find them in Mono Lake, which often has a pH of 10. And so it kind of comes down to the strain and then how much you've acclimated it to those particular conditions. Because we also just sort of have evolution, and with microbes, it works on a time frame or a time scale that's actually applicable for humans. So basically, if we drop a bunch of microbes in and 99.99% of them die, that 0.01% that keeps going is going to reproduce, and then suddenly you start to have a population that is optimized for that condition. And then that brings me to some maps I put together. Can you see the map? This is actually the better one. So this is pulling data from that Holly 2025 paper where they look at a bunch of different deposit types. And so the numbers and the size of the circles are based on the rare earth element concentrations for deposits of those types. I don't have data that's specific to each mine, but you can sort of start to look. Let me turn off some of the messages, or gold and silver have their own page. You can sort of see here we have Mountain Pass, where they have lots of rare earth elements. So these are some specific elements I'm interested in for a grant application, just because these are well aligned with what the grant is looking for. So that's why you'll see a lot of yttrium and neodymium. And then you can also, in the paper, they mentioned that you could start using gold mines for byproduct recovery of additional elements such as silver and copper and arsenic. And here you can kind of see what the concentration of these elements is thought to be in those mining tailings, as well as for copper. And so just kind of starting to think about what the best location for this would be. One other thing to consider is just sort of the other needs of the microbes. So in an ideal scenario, you could do this in an outdoor setting where you could be using the energy from the sun to allow the microbes to both fix carbon and at the same time start pulling this metal in. One of the studies I looked at showed that they can often hyperaccumulate the metals to a point where you can no longer use that biomass as like a byproduct. You need to just sort of burn it to release the metals, which you can then kind of further extract. But as the metal concentration decreases, the biomass being produced is also potentially applicable in like a variety of other scenarios, such as like a substitute for plastics. So kind of the next steps look like taking these mixotrophic biofilms that we know can accumulate the metals and really starting to engineer them for stability under kind of these other environmental extremes, such as pH and salinity. We want to create a database of metal binding moieties in these extracellular matrices. So you can start to connect either strains or specific genes to the accumulation of specific metals, and then start developing a screen for specific metals, particularly the high or the heavy rare earth elements. And then one step, so George Rothman is a professor here at Caltech, and he had a student this summer who's starting to build out a spectroscopy library for these rare earth elements. So not all of them have kind of clear signals, but a few of them have really sharp peaks, which could be potentially used in that screen to start analyzing which specific strains are optimal for doing the bioaccumulation of those